Welcome you all to this course on electron diffraction and imaging. In the last week, we have covered some aspect of energy dispersive analysis, okay. But this part of this analysis, especially is energy dispersive analysis, is used very commonly in most of the electron microscopes to find out composition of the element. So, I thought that we will have a expanded class where we cover this part of it in detail. Okay. Let us first start looking at how the electron beam interacts with matter. Okay. As the electron beam falls on the sample surface, okay, depending upon the thickness of that sample, we assume that the sample is a very thick sample. Then the electron beam will be scattered back elastically without losing any energy. As the electron beam hits that sample surface, secondary electrons could be emitted from the sample surface. The electrons can lose energy by inelastic processes, and this could lead to X-ray emission from the sample surface. Okay. Then the whole electron could be completely absorbed in that sample. This could give rise to specimen current. Suppose the sample is thin and the energy of the electron beam is very high, then the electron beam can come out through the sample, okay, and these electrons are called as transmitted electrons. These transmitted electrons could be elastically scattered electrons which have given. Then the other aspect is that some part of this electron could interact with the atoms and inelastic scattering could take place. This inelastic scattering could be that is by electron phonon scattering, or it by plasmon scattering, or by ionization of the atom, especially removal of electron from core levels, okay, so that fixed amount of energy is lost by the incident electron. These are all inelastically scattered electron, but when this inelastic scattering process takes place, okay, the consequence of it is that the ionized atom has to come back to a ground state. They result in the form of X-ray emission, okay, characteristic X-ray emission, or in the form of Auger electron emission. And another important advantage with electrons is that electron beam can be focused to a very small size, because of which we could get using characteristic X-rays information about the composition of the sample surface from very small areas of that sample. Let us look at what is the phenomena which takes place. Okay. When an incident electron beam falls on that sample, okay, we assume that this electron interacts with an atom, knock out an electron from the K level. Okay. That is, we have generally, if you look at the line diagram, we have a K level. There are 3 L levels are there, L2, L3. Then there will be 5 M levels will be there. Suppose the incident electron is hitting on that sample, okay, with an energy E0, okay, and generally in an electron microscope the energy is of the order of 100 keV to 300 keV is the energy of the incident electron beam. We assume that it knocks out an electron from the K level. So, when an electron has been knocked out, electron from this L level could come down to fill this vacancy, okay, and when this comes down, the difference in energy, okay, between Ek minus El, this comes out in the form of X-ray, which is called as H nu. So, this since the electrons moving in different levels, they have got specific binding energy associated with it. The energy of the X-ray, energy of this characteristic X-ray is fixed by this transition. Okay. In this case, what is essentially is going to happen is that if we measure the energy of the X-rays which are coming out from the sample, from that we can find out what is the element which is responsible for this X-ray emission. So, essentially using this characteristic X-rays, we can identify the elements which are present on the sample surface. So, we assume that X-ray is coming out. Okay. the energy of this X-ray h nu is Ek minus El. But what is essentially important in this process is that this is not the only process which can happen. When a core ionization has taken place, okay, electron this energy electron from this level has come down. Okay. When this has happened, a vacancy has been created in this level. Instead of an X-ray coming out, okay, this difference in energy could be used to knock out possibly an electron from this level, and this can come out. Suppose the binding energy of this electron is L2, then the kinetic energy of the electron which comes out will be Ek minus El minus, I think I will put it as L2. So, this is the kind of, so kinetic energy of the Auger electron depends upon the various energy levels. So, kinetic energy of Auger electrons is also characteristic of the particular element from which this emission is taking place. So, Auger electron also could be used to find out the composition of the element. But what is important in this context is that once a vacancy has been created, these are all the two processes by which, okay, the atom could come down to the ground state. Okay. Both has a different probability or the yield for characteristic X-ray emission as well as the Auger emission, that sum of that should be equal to 1. Okay. We will come back to it shortly. So, essentially there are some transition rules which has to be followed, okay, when photo emission, X-ray photo emission takes place. These rules essentially is that the delta K, delta L, the angular momentum, this should be equal to plus minus 1. This is the rule which is followed. In this table, I had given that assignment of the different levels, okay, and what is the type of designation which is given for the various levels. This is what is being given. Okay. In the next slide, this is with respect to copper. I had given the energy level values. Okay. And in this particular table, what is essentially is being given is the energy of the various K alpha radiation or L alpha radiation or M alpha radiation for different elements. Okay. So, essentially if you look at it, if the transition is from vacancy is created in K level and an electron from L level comes down, then we call it as the K alpha. Okay. If it is from M level, that can also happen, K alpha 1, alpha 2, similarly K beta peaks will come. Okay. Similarly, the vacancy is created in L level, okay, and electron from a higher level M level comes, L to M, then this we call it as an L alpha, okay, type of a transition. These are all the designations which are used, okay, for the various transition. But what is essentially important here is that suppose we take the case of a calcium, okay, here the energy of the K alpha X-ray is essentially 3.69 keV, okay. But if you look at the energy of the L alpha X-ray, it is 3.41. Okay. Similarly, if you look for copper, okay, 8.048 is the energy of the K alpha X-ray, okay, whereas the L alpha X-ray is essentially 0.93. So, compared to K alpha, the L alpha has got very small energy. Okay. Only even for elements like gold or mercury, if you look at it, there the energy of the K alpha is of the order of 60 to 70 keV and the L alpha has got energy close to 10 keV. Okay. Now, as I mentioned, there are two processes by which the atom can come to the ground state. One process essentially is X-ray, characteristic X-ray emission. Okay. Characteristic X-ray emission this is also called as generally used the fluorescence. Okay. The other is Auger emission. Okay. And these are all the two processes by which the atom has to come to ground state. Okay. That means that the probability of both the process to take place, if we take the sum of the probability of both the processes, okay, W for X-ray plus W for Auger, this should be equal to 1. Okay. The question arises, why I am talking about all these things? Because when we wanted to find out quantitative information about the elements which are present on the surface, this information about the yield and all these things are very much important. Okay. Before we go further, let us look at when the electron beam enters on the sample. Okay. What are the types of processes by which the electron can lose energy? Okay. Suppose that sample is quite thick. Okay. Very fine beam of electron we put on that sample surface. Okay. The secondary electrons are emitted, okay, from a very small region of the sample, very close to the surface. Okay. Generally it is almost right from the surface the secondary electrons are emitted. Okay. And generally the energy of the secondary electrons is of the order of 0 to 50 electron volt maximum energy. Okay. Then Auger electrons are emitted from the sample surface. Okay. These Auger electrons generally come from a depth of about 0.4 to 5 nanometers. Okay. Then the backscattered electrons comes from a sufficiently small depth, that is, these backscattered are the elastically scattered electrons which are coming from a larger depth of that sample, and then characteristic X-rays are coming from much larger depth, 1 to 3 micron. And if we take because when a primary electron beam has entered, finally it has to lose all its energy. The energy it loses, okay, depending upon what is the range which it has, and the range is quite large. It is of this order, 3 to 4 microns in this case. So what we can make out is that as the electron beam falls on the sample surface, signals, secondary electrons are generated from a depth which is very small. Auger electrons are also generated from depth which is very small. Backscattered electrons comes from a depth which is large, and if you look at the size of the region from which the signal is coming, even though this is the beam size, it is coming from a larger region. So that means that the spatial resolution becomes poor, and the depth resolution is also quite large, and X-rays come from deep within that sample. Okay. So this is about 1 to 3 micron. The same thing is what is being shown here, but when these X-rays are being produced, what is essentially important is that X-ray has to finally reach the detector without losing any energy. Then only we can accurately determine, okay, what is the element which is responsible for this X-ray emission. If that X-ray loses energy continuously, we will not be getting a peak, and we will not be able to identify what is the element which is responsible for this X-ray emission. This generally goes into the background. So there is a depth from which the X-ray comes out, and not only that, as that X-ray comes out of that sample surface, part of this X-ray, okay, is being undergoes absorption. So that means that suppose this contains about something like 1000 atoms, maybe around 100 atoms have the X-rays which are generated, 100 atoms have lost their energy. So the number of the counts which corresponding to a specific value of energy gets reduced. That means that the composition analysis, it introduces an error. So we have to account for all these factors to find out, okay, what is the exact composition of that sample surface. Similarly, fluorescence is the process in which, as the X-ray comes out of the sample surface, in addition to the absorption, okay, if it contains another element, okay, this X-ray can knock out an electron from the core level in that, okay, and can give rise to that other element, okay, the second element which is present to give rise to characteristic X-ray. In that process, part of this original X-ray which has been generated from this volume where the electron beam falls, there is it getting reduced, Okay. This will also lead to error, or we have to compensate for all these things to find out the actual concentration of that sample. Okay. But this is a case which is being shown where suppose the sample becomes extremely thin, like in the case of a TEM. This is the case which we see in the case of a bulk sample, in the case of an SEM or electron probe microanalyzer. In the case of a TEM, the sample thickness is generally of the order of maybe 10 to 100 nanometers maximum. Okay. So, because of this, okay, the absorption and fluorescence is going to be very small. We will talk about it a little bit later. Okay. Suppose we wanted to quantify the signal which is coming. Okay. What are factors which we have to take it into account? Okay. That is, as we have seen, the beam is the X-ray. Suppose we assume that X-ray is being generated from this volume of that sample. What is the total number of atoms of a particular species which is going to be present in that region, okay, per unit volume? That is what N tells. Okay. And I0 is the current density, okay, or the number of electrons which are falling, or the rate at which the electrons are entering into that sample. Okay. These are all the various ways in which this I0 could be represented. As this electron passes through it, not all electrons are going to give rise to inelastic scattering. Only a small fraction gives rise to inelastic scattering, which results in core ionization of that atom. Q is the factor which defines the efficiency of this ionization of that atom. Okay. Then, as I mentioned, when a core ionization has taken place, okay, then what is essentially going to happen is that all this core ionization does not result in characteristic X-ray emission, only a part of it. So, that is what is given by this factor omega x, which is called as the characteristic X-ray yield. Okay. And then another process which has to take is also A is called the specific transition probability, because we know that electron can come down to a ground state either from this level L2 or L3, both the levels it can come. Each has got different specific probability. That is why we know that between alpha 1 and alpha 2, if we see that one is a 10% of that other. So, that factor also should be taken into account when we try to quantify and find out what is going to be the intensity of the photons which are coming out of that area. Okay. So, these are all the factors which we have to take it into account. Okay. This is as far as the generation of that X-ray is concerned. Then the other aspects which is going to we have to take into account is that when this X-ray is going to come out from this region. So, what we have written this formula essentially I equals N into I0 into Q into omega x into A. Okay. This is the formula which we have done. This tells us how the amount of X-ray which is generated within this volume. Is all this X-ray going to come to a detector or not? That is the next question. Okay. This X-ray as it comes out, this X-ray could be scattered by various processes, okay, and it can lose energy. One is by the electron retardation, okay. It can give part of that energy, okay. The electron will be elastically scattered a little bit, so the X-ray loses energy. There are various effects. So, this is what is called as an Z. We just take the term as this is the contribution from that. Then the next term is that as that X-ray passes through the sample, we know that there is a, because of various processes, absorption, fluorescence, there is going to be a reduction, okay, and that is the term which we call it as an A. And then fluorescence is that another one which is responsible for it. Suppose if you take iron and then if you take chromium, okay, then what is going to happen? The chromium fluorescence can take place, so the ion signal could come down, a factor which you have to take into account. This is what essentially. So, if we take all these factors into consideration, then what is going to be the signal which is going to reach the detector is going to be this multiplied by these factors. So, this is what the signal which is going to come. Okay. Okay. So, but to get quantitatively what is going to be that signal, theoretically if you try to look at it, we should know Q, omega x and A, all these factors which we require. It is not very easy to get this information. Okay. We can do some experimentally we can determine this, which we will discuss shortly. Okay. Suppose we compare this, one way in which we can get this information is, suppose some concentration of the element is present in this region. I can use a pure standard. We know that 100% X-ray emission, whatever is the information, the concentration has to be 100%. Okay. If I compare between these two, okay, that is what essentially which is being written. The concentration, this is N is that equivalent to concentration, Cx by the standard sample if I take it, this ratio of the peaks should be equal to the ratio of the concentration, the elements which are going to be there, provided these terms are also going to be there, correct, multiplied by the ZAF correction also will come. Okay. But generally in an energy dispersive spectroscopy which we consider in an electron microscope, okay, since the sample is thin, absorption could be neglected. Similarly, fluorescence effect is also going to be small. Okay. If we take that into consideration, this term ZAF will go and only that Z will come into the picture. This is what is going to be the expression which gives what is going to be the intensity of the signal which is going to reach the detector. Okay. So, here we can write N I0, these terms Q, all these terms put together we can write it as a factor Ka for the specific element, okay, or a K we can call it. Okay. That means that this K is a factor which has to be determined. So, this K contains the probability of X-ray transition, okay, X-ray probability of X-ray yield, the transition probability for the specific peak which we are looking for, then the Z which corresponds to the atomic number of the element, how it reduces the signal strength, and then Q is the probability for ionization, core ionization of that sample, all these factors. Okay. So, this is using a standard, if we do it, these terms will going to be that same, okay, as apart from the number. So, that way using a standard we can comparing it, we can get the concentration very accurately. That is one way. That means that for suppose a sample contains 10 elements, we know all the elements in the periodic table, we should have a pure elemental standard for all of them, and we have to maintain the identical current to measure this intensity, which is going to be quite a tedious one. So, most of the time because of this what we do is that we use a standardless technique which is essentially nothing but the relative concentration. Relative concentration, what we do is that suppose n elements are present, okay, the concentration of all the elements, the Ci should be equal to 1. This is the philosophy which we follow. Okay. In such a case, let us assume a case where there are only 2 elements are there. Okay. Then what will happen? The concentration elements A and B, Ca plus Cb should be equal to 1. Okay. We are going to get a signal from Ca, we can write an expression like this. Okay. Similarly, we can write another expression for Cb. If we take the ratio of it, okay, then this is the sort of a term which will come, where this term corresponds K corresponding to element A, 1 corresponding to element B. So, this ratio KAB, this is called as the elemental sensitivity factor. This factor is not a constant, it can vary from the geometry of that system. Okay. From 2 different microscopes, depending upon the detectors you can have 2 different values, these are not that same. The simplest way in which one can do it is theoretically whatever the values which has been calculated one can do it, but that does not give the correct values. It is better to find out the elemental sensitivity factors. Okay. This factor KEAB is called as the Cliff-Lorimer factor, where we are not using any standards. Okay. And in this case, in this particular case, what we have assumed is that we have not taken the detector efficiency into account. Generally, what is in a detector efficiency is also added epsilon A and epsilon B for the 2 elements. So, then that completes this expression, and this tells us this is what the KEAB which is going to be. Okay. I have already mentioned for 2 elements, suppose 3 elements are going to be there. Generally what happens most of the time, we use essentially either nickel based superalloys or stainless steel or aluminum alloys, where one concentration of one element, matrix element is very high, others are small. So, we can take that as a standard, and with respect to that we can find out the ratios. Okay. So, what is in fact what is essentially is being done is that this experimentally one can determine, okay, KEAB with an equipment for various elements, what the value for the same identical conditions you have got it. With respect to a particular element which we take it as, we can take the ratio for each one of them and try to find out what the value of KEAB is going to be. Okay. This is what essentially these tables are available, okay, which are there library, which are there in the softwares which is being used by most of the commercial softwares which are available. Okay. So, essentially this factor, suppose 3 elements are there, CA by CB, CB by CC, then we can have CA by C. So, these sort of factors which are there from the tables which are available here, if you look at it with respect to concentration of the element C, okay, we have taken this ratio and calculated what the Cliff-Lorimer factor is going to be. Okay. That means that the ratio of the concentration is not the same as the ratio of the intensities. There is a factor which comes into the picture. Okay. So, in experimental condition, what is normally being done is that suppose you have a sample, okay, you assume that it is a single phase, that is where one can do this experiment easily. Then find out the composition very accurately using either wet chemical technique or electron microprobe, so that we know what is the concentration of the element, and then that same sample thin down in a TEM, you look at it, find out what is going to be the ratio of the intensity of the peaks which are going to come. Okay. And from this expression we can find out what the value of KEAB will be. Okay. That is essentially how we can find out these Cliff-Lorimer factors accurately. Okay. So, we have so far we have talked about how to get the relative concentration as well as the absolute concentration, how we can determine what are the terms which are involved. That briefly we have discussed. I have not gone into the more details of it. Okay. That you can look into the standard books which are available, which gives it in great detail. Okay. In an electron microscope, let us come back to a microscope and see how exactly physically where is the detector, where exactly is the detector is placed. Okay. In a microscope, this is the pole piece. Okay. There is some gap. Normally the gap is around 2 or 3 millimeters, the pole piece gap, which is going to be very small. This sample is there at the middle. Okay. And close to the, as close to a pole piece, the detector is being inserted. Okay. And the detector is inserted in such a way, okay, that the maximum solid angle it submits to collect, that is then that is what is going to define decide the efficiency of collection of that X-ray, because the X-ray is emitted from the sample in all the direction. If you look at the X-ray which is emitted in this direction, the absorption is going to be maximum. If you consider the X-ray which is going to be emitted in this direction, absorption is minimum. So, up to some certain angle, okay, the absorption is very small, which can be neglected. So, that angle is, in the case of a microscope, it is about 30 degrees. Okay. So, that is what essentially is being done, that for that essentially the detector should be kept at an angle so that it submits an angle, this alpha, which is around 30 degrees. Okay. This is how, and one has to be extremely careful, because finally the chemical analysis essentially is something which we have added as one which gives more information, but the basic job of microscope is to give the best image resolution. Okay. So, that one cannot compromise. So, one has to introduce the detector in such a way that it does not affect the performance of the pole pieces, because no way the pole piece should be affected. Okay. That puts some limitation on what the sort of analysis which could be performed using EDS in a microscope. Okay. If you look at the type of a spectrum, an ideal spectrum, if you look at it, okay, because we have a detector, the signal is coming, okay, and we are trying to analyze that signal. Okay. From whatever we have discussed so far, essentially the characteristic peaks of all the elements which are present in the sample surface, okay, from that volume should reach the detector and it should give rise to some peaks. Okay. That is what we should observe in the ideal case. Okay. What is it which is happening here? You can see that that is not the case which happens in real cases. Okay. And generally the signals which are being generated, okay, if you look at the line width of these X-rays, they are going to be from 1 to 10 electron volt. Okay. But what is the normal resolution which we talk about in an SEM, that is EDS attached to an SEM or a TEM, we can get it. It is about something like 120 to 130 electron volt. That means that resolution is quite poor. Okay. We will talk about a little bit later what is the reason for such a poor resolution we get it in an EDS technique. Okay. Then there are many other peaks also which come, which are called as spurious peaks. Okay. All these things we have to account for. So, when we wanted to do a quantification, the first and foremost thing is that even in an ideal condition, the background could come, could come from Bremsstrahlung and the noise. So, the signal to noise ratio we have to correct for it. Okay. So, the Bremsstrahlung has to be eliminated from the spectrum which we have obtained, and then from the peak to noise ratio also we have to get that information. Then only we know how many counts which are coming from exactly from the sample, that is from the elements which are present on the sample and not due to Bremsstrahlung or not due to a background, correct, at that position. Okay. So, in a real EDS spectrum, if you look at it, that is where one has to be extremely careful, because most of the softwares which are available, they give some calculation analysis, but one should be take sufficient care to see to it that all the spurious information which is there is eliminated before one does quantification. Okay. For which, what are the things which can come? One, an escape peak. Escape peak is what it is called as, it is due to appears in a fluorescence in the detector. Okay. That is as the X-ray beam with a particular energy. Suppose we assume that X-ray from a copper K alpha, okay, X-ray is entering into a detector. The detector is nothing but a silly detector which is normally used. Okay. As it enters into it, initially itself that is called as a region as a dead layer where no information is being collected. In this layer, as the X-ray enters, it can cause a fluorescence here. So, if it causes a fluorescence here, that means that it ionizes the silicon K alpha. So, some part of the X-ray comes out with losing some specific energy. Okay. That means that the reduction in energy of the copper K alpha has occurred, and then copper K alpha energy minus this energy corresponds to, it's around 1.74 keV. At that position you get another peak. So, that is a spurious peak. You will say that silicon is present, but the sample may not contain silicon. So, this is one thing which can happen. Then another what it can happen is the sum peak. We assume that every X-ray signal which is generated, okay, is by a process, that is this process we assume that as an each electron beam enters, okay, the current is such that the sample is so thin that when it undergoes only one process, scattering process which undergoes, okay, an X-ray of a particular energy is generated, and that is the only X-ray which is being detected. When the next generation comes, it generates characteristic X-ray from some other element that comes separately, it is being detected. So, each is done sequentially, okay, that is what is being done. Suppose the count rate is high, what can happen is that X-rays are generated simultaneously from two regions, both of them reach the detector, okay. Both of them, the signal processing will not be able to identify them as two separate ones. So, essentially how does that detector detects it? As the X-ray passes through this thin region, okay, it produces electron hole pairs, and that requires in the case of silicon about something like 3.8 electron volt. Then if you know the energy, we can count how many electron hole pairs will be produced. If simultaneously they produce, the total charge which we collect it, okay, that is what we count it as corresponding to specific energy of the electrons. So, if two X-rays from the same element, okay, reach simultaneously two X-rays, then that will be counted as a peak with double the energy. That will give rise to another peak. It is a spurious peak. Okay. Then what is called as a coherent bremsstrahlung, that is especially on a crystalline material, when the beam is along the specifically along the zone axis, okay, and arranged, then the beam enters. Bremsstrahlung is radiation which is being produced, okay. Because of the coherency of the beam, this can give rise to some peaks which are appearing at different energies on the overall background. That is one process which can take place. Another is a spurious peak. What is a spurious peak? That is, as the electron beam enters into the sample, that is, we have the this is the lower pole piece, upper pole piece, and this is the lower pole piece. Okay, this is where the sample is there. We have the detector which is kept here. Okay, the electron beam is falling onto a sample and coming out further, but in that process there may be a aperture here or the pole piece, copper winding is there. Everywhere this electron beam can hit and X-rays can be produced. All these X-rays could reach this detector. Okay, they are also characteristic X-rays. So, this will give rise to peaks corresponding to them, because finally when we look at the spectrum, try to find out what all peaks which had come. So, this requires some typical alignment to see to it that the spurious peaks do not come, but we have to be careful about it to identify that the peaks which we have got it in that sample are what we feel the peaks, whether they are spurious peaks or whether the peaks corresponding to actually the one which has come from the area in which the electron beam has fallen. That one has to be careful about. Then the fluorescent peaks which can come. All these are the factors. What is the effect of the fluorescence peak? The fluorescent peak will also increase the intensity of one peak and reduce the intensity. That is, suppose this fluorescent peak matches with another element. So, intensity of that element peak will go up, and the intensity of the original element from which the X-ray has been produced, that will come down. Okay. So, this is just showing some examples of peak where copper K alpha, and it is around 8 keV, and you can see that around 6.2 you have another peak comes, escape peak. Okay. This is an escape peak. Some peak is here, it is a magnesium peak, okay, in a sample, and since the, especially when the count rate is very high, that is where you get all this, because for this purpose we have to reduce the count rate considerably. Okay. Now you can see that there is a peak which has come corresponding magnesium, some peak comes. This may correspond to some other element. So, we will think that another element is present in that sample, which may not be the case. So, one should understand all these things and make correction for it before we try to do quantification. We have to choose what all the elements which has to be considered, what all the peaks which have to be considered, and we have to assign them that this corresponds to a particular element. In that process, we have to eliminate all the spurious effects. Okay. This is like here you can see that the copper L alpha and this is the copper K alpha peak. In between, this is an escape peak. There are some lots of peaks which are coming residue. These are all the coherent Bremsstrahlung peak. This comes from as the incident beam falls onto the sample, correspond close to this that is one of the reasons why we always say that one should be far away from dynamical condition when we wanted to get wanted to do EDS analysis to get, then only you can get true composition. Close to small index zone axis pattern, okay, we will get a lot of not only spurious peaks, we do not get the correct information about the composition of the elements present in the sample surface also. This I will come to shortly. Okay. Okay. Where do the spurious peaks come? As I mentioned that the electrons when it passes through the sample, this is where the specimen generated continuum X-ray is there. Okay. Then these electrons, because it is being focused to a point on the sample surface, then it diverges, then it may be hitting so many places. From here also X-ray will be produced. This X-ray when it is produced, it passes through it, it will be hitting the thicker region of the sample, it can produce fluorescence. Okay. There are so many ways in which, okay, this information it could produce. Most of the microscope, if you look at it, the holders which we use are copper which is going to be there. So, even if the sample may not contain copper, but we will get a lot of signal corresponding to copper. The only way this can be reduced is to use beryllium holder, so that low Z elements, essentially the X-ray process of X-ray generation efficiency is very small, okay. And that is why if we wanted to do EDS analysis, the chemical composition analysis of a sample, one should not look at the sample in the normal holder, one should put the sample in a beryllium holder. Okay. And then another important aspect is that generally if we put the, to improve the contrast, we introduce an objective aperture. The objective aperture is either platinum or molybdenum. That also will generate sufficient X-rays and damage the detector. So, it is better to do the chemical analysis. When we do, the aperture should be removed, so that we can reduce the background noise as well as the spurious signals could be reduced considerably. Okay. These precautions have to be taken. Okay. Then I mentioned that if you have to maximize that signal or to reduce that absorption, that to maximize the signal also, that is the detector should be kept at an angle which is greater than 30 degrees. Okay. This could be achieved in two ways. One is that, like in this particular case, it looks like that the detector is perpendicular to the beam direction. But what is being done here is that if you look at it, at the end of it, this rod where the detector is kept, it is inclined like this. Because of this, since the detector is kept like this, inclined like this, the angle which it satisfies, this angle is essentially 30 degree we can maintain. Or the other option is that you can keep the detector coming like this. So, then also the same angle could be done. These are all the two approaches which are used practically to increase the takeoff angle. Okay. And in spite of all these things, the area of the detector is either 10 millimeter squared or 50 millimeter squared. Okay, that is what it is going to be, or 30 millimeter squared. And of the X-ray which is going to come over a solid angle, only a small fraction at a position which we are trying to collect it. So, one has to take as much precaution as possible, so that all the X-rays maximum signal reaches the detector. Okay. Okay. This is a statistical counting process, so statistics plays a part. So far what we talked about it is identifying the signal, okay. That is characteristic peaks which are present in the spectrum which we have obtained. Okay. When do we decide that some peak which appears is not a noise, but it corresponds to a signal? Okay. For that, the statistic what is the background peak, and if the peak height, the intensity is 3 times more than that of square root of this peak height, then we can say that the peak is statistically significant, because with 99% confidence we can tell that that is a peak which is going to be there. That if you look at the spectrum which commercial software give, they give all this information, how these peaks are chosen, but one should also be aware that this is the way in which it is being done. Okay. Then another is, if we have chosen like this, what is going to be error corresponding to each peak? Suppose we count some n number of counts. Okay. If with 1 sigma confidence level if you wanted to count, then the error is going to be n to the power of half by n. It is a percentage. This is how we can represent this. Okay. If it is 3 sigma, 3 times it is going to be there. So that gives the relative error, and we know that this will finally turn out to be 1 by root n, correct. That means that higher the counts the more the counts which we collect, the error is going to be less and less. So in all this analysis, what is essentially important is that we should collect as much signal as possible. Okay. So if 2 elements are going to be there, then we can find out what is going to be the total error, and what is this error going to decide? This is going to tell is that what is the confidence with which we can talk about the concentration of the elements. This is going to tell you that in which significant digit you have to stop. Suppose somebody gives a composition up to second decimal place, that is 25.56 is the concentration. Then one has to be very careful about it, is that is it really possible or not. Okay. As per, if you look at that, then one should know what is the total counts which have to be collected to go to that accuracy, whether that experiment has been performed to that level or not. Okay. These are all very important. Okay. Okay. There are various types of detectors which could be used. These are called SILI detectors, okay. Intrinsic germanium detector, okay. Then silicon drift detectors, okay. Then calorimeters, wavelength dispersive detectors. Okay. Let us take the case of the EDS detectors which are used, which are SILI intrinsic germanium detectors or silicon drift detectors. In all these things, the process by which the X-ray, with characteristic X-ray we detect it is, as the X-ray passes through the sample, we assume that it is being completely stopped, then it loses energy by creating some electron hole pairs, and in the case of silicon the energy is about something like 3.8 electron volt is required. In the case of germanium it is 2.5 electron volt which is required. Okay. That means that for the same energy of the X-ray, the number of electron hole pairs which will be generated is more in germanium, so the sensitivity is high for germanium. So it is, if one can afford to use that, that is good, though it is expensive. Okay. And this process is also a statistical process. There are various other processes by which it can lose energy. So suppose the number of hole pairs which is for a particular energy E, it produces for one X-ray, it may be producing a number N1 electron hole pairs for the same characteristic X-ray. Okay. The second signal which comes, it may not be producing N1, it may be producing N2. Okay. So that means that for the same energy of the incident X-ray, there is a difference in the energy of the difference in the number of electron hole pairs which are being produced, and that means that the charge which is collected is not the same for all the characteristic X-rays from a particular element reaching the detector. This will give rise to a broadening. This broadening is the one which gives rise to that 123 electron volt reduction. Okay. But if we use another technique like WDS, wavelength dispersive analysis, there we can find out the X-ray energy very accurately. Okay. Because there we are not using the energy, we are using the dispersion of the wavelength associated with the characteristic X-rays. Okay. There we can resolve them. Or the other way in which we can do it is called bolometer, microcalorimeter. In a calorimeter, all the energy which comes, we can find out that energy which is absorbed, that will be the same. There also the resolution, this is what is that energy resolution, which is going to be very good. And another is that if you wanted to find out composition of a large area of a sample, in a TEM mode, if you try to scan, the image resolution will go down. It is better if you do in a scanning transmission mode, where we can scan on different area of that sample, and from each area we can collect the spectrum. Okay, we can do a quantitative analysis which is possible. This is all because of the computing power, which was not possible earlier. This is an example where using a stationary beam in a transmission electron microscope, the composition which has been determined from these precipitates, which are of the order of which are very small size, about 0.1 micron size, and we could accurately determine the composition. Here we have used, as I mentioned earlier, that is the composition has been determined from EPMA and other sources independently and in a single phase. That is how this analysis has been performed. Okay. Another is, normally you see that earlier people used to give X-ray mapping, how the distribution of the various elements are done. There what is being done is that corresponding, you put a window, okay, choose a window corresponding to a specific element. When a next signal comes corresponding to that, it is being marked at that specific position as a dot which is coming, a bright dot. But whether that dot is coming from a Bremsstrahlung or a background, we do not know. The present day information, we have all the information which is collected from each pixel, each region. Okay. Now one can remove all the background and everything and try to find out quantitatively what is going to be the signal which is coming, and then we can get it. These plots are corresponding to such, so that we can find, this is in a low alloy steel, how nickel and molybdenum, zirconium are segregated along the grain boundaries. This sort of information one can get it. That is possible in present day micro, because earlier the counting with statistics was using an analog type of a system. Now they are all being done in a digital form. Okay. That is what it has made all the improvements. Okay. Then let us talk about a resolution. What are the types of resolutions which we look for? Okay. We have already discussed, I am just trying to point out. One, since we use an electron beam, a spatial resolution which is important. As I had shown earlier, like in this case, even though the beam, spatial resolution of the beam is very small, as far as X-ray is concerned, this is what the spatial resolution is in the case of SEM or in EPMA. Whereas in the case of TEM, since we use the sample to be very small, the X-ray is coming from a very small region, so spread is very small, so the spatial resolution is very good. Okay. Another important factor is that suppose we wanted to improve upon the spatial resolution, what we have to do it, the beam has to be made finer and finer. Okay. That means that the aberration has to be corrected. If we can correct the spherical aberration, then we can make the beam as fine as possible. So in aberration corrected microscopes, spherical aberration could be corrected. And another is, when we use field emission gun, then we can increase the intensity in the very small region. The current density could be, electron current density could be increased considerably. With this, we could do analysis from extremely small regions of the sample. Okay. then the energy resolution essentially is determined by the detector, that we have no control over it. So, we have to accept that if we wanted a better energy resolution, we have to go for as I mentioned, that borometer. The problem of a borometer essentially is that it has to be after microkelvin, that is the only problem, temperature. Whereas like SDD detectors and all, even with a Peltier cooling, okay, one can operate them, you do not require a liquid nitrogen cooling of the detectors. Here I am just showing an example of how in an EPMA, this is the beam size and this is the volume. Okay. If we wanted about 0.01% concentration which we wanted to detect, then the number of atoms which are going to be there in this case is 3 into 10 to the power of 6 atoms in this volume. Suppose in a conventional atomic analytical electron microscope, 10 nanometer beam size if we choose it, 100 nanometer, the volume excited is 10 to the power of -5. If you use thermionic source, for this 300 atoms are going to be analyzed for this concentration. If you use 1 nanometer beam size and 10 nanometer sample size with FEGS, that this one, essentially almost like only one atom may be present in this region to give this concentration. To get the signal from this, it is not trivial, right. So, essentially as I mentioned, to get more spatial resolution as the beam spreads, if the sample is thin, okay, the spread of beam will be reduced considerably, okay, so that the beam size is the same as the spatial resolution. Then the depth resolution is very important in the case of SEM as well as EPMA. What is the depth from which the signal is coming? That depends upon the primary beam energy as well as the escape depth of the X-ray which is being produced from what thickness. So, essentially like in SEM, it is essentially about 1 or 2 microns. That means that we do not get true surface composition of that sample. And another thing also is that since we do not know what is the thickness of the second phase particle, it is always there is a doubt that whether that entire signal is generated from the full volume of the precipitate or not. Whereas in the case of a TEM, this doubt can be cleared because we know that we are able to observe the image of the precipitate. We know that how much is the thickness precipitate contributes to how much is the thickness. That is, suppose this is the sample, a precipitate I assume it to be a rectangular one, it is going to be here. When the electron beam passes through it, we know how much is the volume X-ray is generated from the precipitate, how much from this. So, we can account for all these things, which is not possible. That is, suppose this region does not contain precipitate, from this region we can find out a composition, then we can apply a correction so that we can find out what is going. These are all things which one has to, depending upon the type of information which we look for, one has to think about it and devise experiments and get the correct information. Okay. Then this determines also the peak to background as well as the peak signal. Okay. That is going to determine what is the minimum detectable fraction. Okay. Whereas in the case of many of the wet techniques or emission optical emission atomic emission spectroscopy and all, where we can detect to a much accuracy, ppm levels we can do it, but that is not possible in this. Here maybe at best if we can do 1 atom percentage to 0.1 atom percentage, that itself is considered as great, but for that we have to take a lot of precaution. And another is for high Z elements is where we can use this to find out the composition with some confidence, because low Z elements below 1 keV absorption is going to be quite high. We may be able to obtain a peak corresponding to a particular element, but to find out the composition accurately is going to be, it is not a trivial task. That requires a lot of extra care which has to be taken. Okay. Another is very important is what is called as an alchemy. This is essentially if we make the beam into a very fine focused beam and channel through, that is like in the present day microscope with FEG and aberration corrected microscope, we can have a beam of the order of 0.1 nanometer. We can make the beam pass through a particular zone axis. Okay. Then depending upon which direction it passes through, okay, we can make it see some particular element, or some element may not be the contribution be. That is the what is being shown here with theta equals theta 1, its S is greater than 0. Okay. You can see that the corresponding to A, B, okay, corresponding to A element, B element, and that X, the peaks corresponding to them, the intensity of the peaks come. And when S is less than 0, here you can see that the peak height has changed, okay, in another direction. Using this information, we could identify which position the atom is occupying in the lattice. This is called atom site location by chemical analysis. Another thing also which is very important is that when the beam, electron beam is passing through the sample, okay, depending upon which Bloch wave is excited, okay, either the electron concentration could become very high on the atom surface, or it could be high in between the atom surface. Depending upon that, if electrons are going to be distributed, suppose these are all the atoms which are there, okay. Suppose this is the way the electron distribution is going to be there, one of the Bloch waves. That means that since the intensity of the electron is maximum here, possibility of interacting with the atom is very high in this particular case, okay. So the signal strength will be there. Suppose it is the other way around, so this is a 180-degree phase shift. Here the concentration of electron is going to be concentrated more between that region. That means that the interaction of electron with the atom is going to be less. So the X-ray, characteristic X-ray generation probability reduces. This is what it is going to happen when we are close to Bragg condition. That is one of the reasons why I mentioned that if we choose, one should be far away from Bragg condition to find out the true composition of the sample surface. Okay. That is essentially avoid dynamical condition of diffraction while doing EDS. Okay. I will stop here now.